All right, we are now one step away from finishing our integration series. We have a couple of example problems, but after that, we will now be clearing our diagnosis of can't integrate.
Isn't it wonderful?
That after all this time, we are coming together to actually get better at math. But we still have this to go over, so let's get this over with fairly soon with some problems. So to begin with, recall that we are doing our practice on the inverse trigonometric functions in the integral. And for something like this, with the 1 over the square root of 9 minus z squared, what will come to mind in our note is that we are looking to keep the form of the integral of 1 minus u squared in the denominator inside the square root, and this should be a du. And so, because of that, this note here will take us that we are going with the inverse sine of u plus c. This form matches that form that we have in the problem. But of course, there are a couple of issues though. We have a 9 there instead of the normal 1, right? And there is no compromise. There needs to be a 1 inside of that square root to even do this type of integral. So our first step here is that we are going to have to run a little bit of a factor here to remove a factor of 9 from the square root on the bottom. But then that means that we'll end up with a 1 minus z squared over 9 in that square root. Okay. Our algebra still holds up that if we distributed back that 9, we'd match exactly what we started with. So there's no change in value there. But what that also means for us is that we can then take out a coefficient, thankfully, because 9 can be taken away from the square root, and that will result in a positive 3 root 1 minus z squared over 9. Okay? Now, things are looking pretty good now that we have that 1 taken out, but that also means that we can leave the coefficient of 1/3 off to the side, and then we have our remainder here of dz of now square root of 1 minus. Now the next step in our minds though is that we have z squared over 9. That doesn't exactly match the u squared in our notes there.
What shall we do?
I don't know.
Well, if we gave it some thought here, we realize that u squared doesn't necessarily mean that it has to be just some variable squared. U squared just means it's any sort of value or function in this case that just has to be all squared. Well, z squared is one part of it. It already is squared, but also 9, think about it as well, 9 can be square rooted as well. And so we can factor this in a way that it is z over 3, all of it squared. We see that now? We call the entirety of that fraction squared, which will match with the form that we need to run the integral. I say that's pretty good. And so with that, it looks like we have just about everything we need to run our first proposed answer, right? We have 1 over 1 minus z over 3, all that squared in the square root. That matches the form that we had in our note. And so we'll leave that 1/3 waiting. We have the inverse sine, and now what must go inside of that sine function is what exactly was being squared, which is going to be z over 3 plus c. Okay, not too bad. But as always, we can't exactly square this answer away unless we check to make sure that this is the correct answer itself. So let's go ahead and take that derivative of our proposed answer, and let's have a look. Right, we have a 1/3 waiting for us. Then that sine inverse of z over 3 will then give us the lovely ratio of 1 over the square root of 1 minus all of z over 3 squared. Okay, but not quite done yet there, that we need to multiply a 1/3 thanks to chain rule plus c. Okay, we have matched up almost everything, but now we have a little bit of an issue because this 1/3 does match with that 1/3 that we started with. Again, this matches what we had as well before we ran the integral. But then of course we have the issue of this. Where did that come from, right? An additional 1/3, which we do not wish to have, right? That additional 1/3 needs to be taken care of by going back to our answer, because again, everything here matches. This is all good. We like all that. We don't like that additional 1/3, So in order to cancel that, we go back to our proposed answer here, and we just need to multiply a 3 as a new coefficient. Everything else matched. We just need to do some coefficient fixing. But how convenient that we get to remove that 1/3 coefficient that we started with from our first proposed answer. And our resulting answer is a very clean inverse sine of z over 3 plus c. Okay, so if that's our second answer, let's run through another check here. So the idea now is that we remove that 1/3 coefficient, and we end up with 1/3 1 over the square root of 1 minus z over 3 squared. Now, if we want to really make sure that we've matched everything up, we can go ahead and start putting everything back to match exactly the form of what we began with. So it'll be 1 over the 3 multiplied by the root of 1 minus z squared over 9, by now squaring that fraction that we started with in the bottom there. The 3 can re-enter that square root, not as a 3 now, but as a times 9 form, because it's going inside of a square root. So again, a whole 3 will obviously be equal to a root of 9. Again, a little something here just to make sure that we do remember. Again, whole 3 is the same as a root 9. So going into the root, it needs to gain that value to get in there. And so with this, with 9 being multiplied across, we have the square root of 9 minus, and the 9 will cancel out with that 9 in the denominator. So it's 1 over 9 minus z squared, exactly what we started with from the beginning. So that answer can indeed be squared away as a great result of our second iteration of this inverse sine integral. But I think we're pretty good for it to see that this indeed works out. Let's get to the next problem. Ah yes, and here we are, our final problem for this series. So this looks fairly simple enough, and I know that some people might wish to jump the gun on this guy, just thinking that, oh, how great! We got x squared plus 1 there and an x plus 1 on there. This is light work, man. All we need to do is then take our note here. Oh yes, if we just take the natural log of x squared plus 1 and then take that derivative, this form looks pretty nice to me. We just go, oh yes, we got 1 over x squared plus 1, and then we multiply a 2x, and then, ooh! Looks like your hubris got the best of you, didn't it? And the fact that there is no, where's the plus 1? Where'd it go? We need that. That's not going anywhere. And so this is one of the great tricks about dealing with fractions with multiple components in the numerator. We can first, before we run off and make all of our notes about which rules we wish to use, we can simply go ahead and start splitting up this integral across everything that it was added to make our lives a little bit easier. So we can actually split this across x over x squared plus 1, and then also 1 over x squared plus 1. Now we have two guys, which forms look a lot better than what we have. And would you look at that? Your running into the wall wasn't so bad after all, because this form now does match a lot more with exactly what the natural log of x squared plus 1 really is. Oh, I knew that all along. I was just testing you. Yeah. Don't worry about that. What we do need to worry about is this next guy here. Do you happen to know what form that needs to be in? 1 over x squared plus 1? If only we were doing our practice. The fact that the integral of the inverse tangent of u du is indeed that exact form. The 1 over 1 plus u squared plus c. Now, if you were really paying attention, you'd realize that this is indeed in backwards form. It's actually the other way around. The derivative of the inverse tangent will give you this ratio and not the plus c at the end. See, we got to make sure we know both ways of doing this. So given that we are taking the derivative backwards into what we started with the integral, the reverse will be true. See, now you got to really make sure you know which direction to go, because the integral of 1 over 1 plus u squared du, now this will give us that inverse tangent rule plus c. This guy is indeed the one that we're looking for the whole time. Okay, so it looks like we got everything really matched up here. The natural log, of course, looks pretty good to us. It's just that we don't want that 2x. So in order for us to do that, let's just make sure we're multiplying this by a 1/2 coefficient to make sure we're locked in on the right forms. A little bit of a mess here, but still should be fairly legible for us to understand what each of these guys will turn into. And of course, right from the very beginning of our lecture series, doing addition rule just means that we can do them one at a time, and we worry about adding them later. So let's start off with the x over x squared plus 1. So remember that we took our note, that's the natural log of x squared plus 1. Okay, and then of course, because the x squared has that chain rule of 2x coming out of it, remember that 2x that we took a note on earlier, that must mean that we need a 1/2 coefficient slapped onwards onto that natural log. And then let's add that with our second part of the function, which is going to be that inverse tangent rule. So it will be the tangent inverse of x plus c. There. That looks pretty good to me. But of course, before we do anything else, we must run a derivative as a check. Always and always and always, the whole purpose of integrating is that we can always check with its derivative. So let's run the 1/2 and then the natural log. Again, that will give us a new ratio of 1 over x squared plus 1. And then chain rule after that will multiply by 2x, waiting for it. And then let's add with the 1 over the inverse tangent. Now is going to give us 1 plus x squared. And then the plus c is now going to go to 0. No chain rule of a tangent because it's just x inside of it. All right, so let's go ahead and cancel out that 2 there. So we get x over x squared plus 1, and then a 1 over 1 plus x squared waiting for us with the tangent. And again, these two denominators do match up exactly. So we can combine this into one simple large fraction. Now, would you look at that? It matches up exactly with what we have right from the start. Very good. And so we have exactly what we need to mark this off as an answer. Again, just a few notes, a few ideas, putting them together after all that we've gone through, and now we finally finished all of this. All right, so this really does conclude our first lecture series, but we still have so many more topics to study for the AP exam. So starting Monday, we shall begin our new series on definite integrals. Ooh, yes indeed. We're going to start dealing with all those good stuff of integrals with, wait for it, numbers waiting for us. Oh dear. And we have a lot of theorems and a lot of different rules that we're going to keep in mind for this, and we'll be back next time on that. As always, I am streaming twice a week on Tuesdays and Thursdays, and so you can either catch us for the next video or on the next live stream for any questions you have that we can answer live. Other than that, this will really be the end for our first series, and we'll see you on the next one.